Hello, today we're going to talk about Reactivity 3.2.3 and 3.2.4, and this has to do with relating redox reactions to elements in their position on the periodic table, and how we're going to compare the reactivity of those different elements. So let's talk about nonmetals first. For the most part, when we're dealing with redox reactions, the nonmetals are going to be gaining electrons from that process. And that's because the nonmetals want to gain electrons to fill up their octet, fill up their valence electron shell. And so gaining electrons is reduction. And we can talk about the reactivity here in terms of electron affinity. So let's look at those halogens. And so we've got fluorine, chlorine, bromine, and iodine. And fluorine is going to be the most reactive of the set. It's going to attract electrons to it the best because it has the least number of electron energy levels. So the protons are better able to attract in electrons from outside due to the small number of energy levels. And then as you go down, you get more and more energy levels, so the atoms become less reactive because it's harder for it to attract electrons to it with the more energy levels. That means that fluorine is going to be the best oxidizing agent of this set because it's going to undergo reduction the easiest, and whatever is reduced is also called the oxidizing agent. Now let's talk about metals. For the most part in redox reactions, the metals are going to be losing electrons to form a cation. Because metals want to lose electrons to get down to a noble gas configuration, and losing electrons is oxidation. And so when we're talking about metal reactivity, it makes more sense to talk about ionization energy because that's the energy required to remove an electron. And so if we look at like the alkali metals, group 1 metals, we have lithium, sodium, potassium, rubidium. And as you get down, your ionization energy decreases. That makes it easier to remove a valence electron. So the more you go down, the greater the reactivity because it has a smaller ionization energy. It's easier to remove an electron. So that's how you can easily compare metals that are in the same group with one another. So while we can use those periodic trends to help us predict reactivity, there are also things called activity series or reactivity series, where they put it in order, the most reactive metals, and they list them down to the least reactive metals. Or in a separate list, they would put the most reactive nonmetals going down to the least reactive nonmetals. There is, in your data booklet, in section 19, there is a reduction potential chart. We're going to really get into what reduction potentials mean in a later section. But for now, it's a pretty good indicator of the activity of certain metals. So, and that's section 19 in your data booklet. Has the reduction potentials. And the ones at the top are the most reactive as solid metals. So even though they're listed as a reduction, like the first one on the list are lithium ions becoming solid lithium. Solid lithium is the most reactive metal. So that means this reaction, the reverse reaction, is going to happen the most frequently, not how it's written, the reverse. But other than that you need to keep that in mind. It's a pretty good list. It helps you can determine which metal is going to be more reactive than the other. The higher ones up on the list are going to react more frequently. There is not an activity series given for nonmetals in the data booklet, so you'll need to use just periodic trends for that. As you go further down, the nonmetals become less reactive. So why is this important? Well, it's going to help us predict whether a particular redox reaction will occur or won't occur under normal conditions. And for that part, we're talking about, for the most part, single replacement reactions. So something like if I have zinc and, let's say, aluminum chloride, and I want to know, is that reaction going to happen without any outside forces? And so this is our solid zinc and our aqueous aluminum chloride. The metal by itself in that reaction needs to be more reactive than the metal that's in the compound. So the neutral one has to be more reactive than the ion version of the metal in order for that to work and transfer the electrons. Now in this case, if we use our activity series, zinc is further down. This one is less reactive, aluminum is more reactive. So in this case, there would be no reaction observed. But if we had solid aluminum reacting with zinc chloride, the aluminum is by itself. It is higher up on the activity series. So it can displace or replace zinc in this reaction. And you'd wind up with zinc by itself and aluminum chloride, with really the chlorine being a spectator ion in this case. So the activity series helps us to predict whether or not single replacement reactions will occur, and the one by itself needs to be more reactive than the element in the compound. Or another way to think of that is the element by itself needs to be more reactive than the ionic version in order to transfer those electrons. Now this is not a balanced reaction. You would then of course need to balance it. I'm just giving you an idea of what's happening to the atoms in terms of their charge or oxidation state. Now you also need to be able to predict reactions using the same method but with acids. Now if you have some metal reacting with hydrochloric acid or with sulfuric acid, those can react to form hydrogen gas and some kind of salt, some kind of chloride salt or some kind of sulfate salt, depending on what's going on. But the metal that's by itself, that's reacting with the acid, has to be more active than hydrogen. And hydrogen is also included on the activity series. So let me give you an example. If I have like zinc reacting with HCl, zinc is higher up on the activity series. So it will be able to displace the hydrogen, and we will form hydrogen gas and zinc chloride. But if I have something like silver and HCl, silver is not higher up than hydrogen. Silver is less reactive, so this will not produce a reaction. So same idea as any of the other single replacement reactions. Use the activity series, compare with hydrogen instead of a typical metal. So now let's look at a couple examples. We want to predict whether the following reaction will occur. We've got our zinc chloride with silver, forming silver chloride and zinc. So you'd need to use an activity series, or in this case you could use, if you have the data booklet, you could use the standard reduction potentials in section 19. And if you find the one that produces solid zinc, and then the one that produces solid silver, I'm looking at it right now, zinc is much higher up on the list than the solid silver. So that means this reaction will not occur, because in order for it to occur, the metal by itself has to be more reactive than the metal in the compound. Okay, complete an ionic equation for the reaction between sulfuric acid and magnesium metal. First thing you should always do is check the activity series. Magnesium is higher than hydrogen, so this reaction will happen. So you will wind up with hydrogen by itself and then magnesium sulfate as the salt being formed. And so that is your complete equation. You should also write the net ionic equation because this acid is a strong acid. It's going to separate from the sulfate ions, and the magnesium will be all by itself. The hydrogen doesn't change as a gas. The magnesium ions will separate from the sulfate ions. Now, if you'll notice, there are sulfate ions on both sides, so I can go ahead and cancel those out. The sulfate becomes a spectator ion. So you are left with hydrogen ions plus magnesium yields hydrogen gas and magnesium ions. Now this section links back to structure 3.1. Why does metal reactivity increase down the main group? That's because ionization energy decreases. It becomes easier to remove an electron, which makes metals more reactive because they're more likely to be oxidized. Non-metal reactivity decreases down a group because the nonmetals have less electronegativity. As you get further down a group, it's less likely for it to gain an electron from the outside because there's more energy levels. So it's less likely to undergo reduction. This last one links to our scientific skills, what observations can be made when metals are mixed with aqueous metal ions and solutions of halogens are mixed with aqueous halide ions. So depending on the activity, sometimes if there is a reaction, the solid metal, you could have a displacement reaction. And so you could see a different solid metal being formed. And depending on the metal, it might change color. So a good example would be something like if copper is being formed, solid copper is being formed as a result of the reaction, you'll see that reddish-brown solid being formed. Or if your reaction is using up solid copper, you could notice that you don't no longer have the reddish-brown solid, but you could have copper ions, which are blue or green. So you need to pay attention to which metal is present or which metal is being used up, and you can talk about color versus the solids or the solutions. And then for the halogens, you need to be aware again of activity, but fluorine and chlorine are both gases. Bromine is a liquid at room temperature, and iodine is a solid at room temperature. And so then we can talk about the difference in state when you have those pure halogens. So you might be forming a new liquid or a new solid or a new gas. You could be using up a liquid, solid, or gas. You could also notice color changes because bromine liquid is brown and solid iodine is like a grayish color. So you could see a color change there as well.